What I've got here is liquid nitrogen, and the liquid nitrogen has a boiling point of minus 196 degrees centigrade. Now, as you see, it's boiling away in my plastic bottle here, and the reason why it's boiling away is because this room is remarkably hot compared to the temperature of the liquid nitrogen. We here are at about 21, 22 degrees centigrade. Liquid nitrogen has a boiling point of minus 196, which is almost as cold as you can get anywhere in the universe. Absolute zero, the coldest temperature in the universe, attainable theoretically, is minus 273 degrees centigrade. Now, one of the golden rules when you have liquids which are boiling is never ever put them into containers which are tightly sealed. Well, that's precisely what I'm going to do now. I'm now going to have these Sprite bottles here, and I'm going to tightly put the stoppers on, and I'm going to gradually put them into these dust bins here. Now, the reason why you should never ever do this is because when liquids boil, they undergo a huge coefficient of expansion by a factor of about 800. I have poured in approximately 100 centimeters cubed of liquid nitrogen into each of these bottles, and that 100 centimeters cubed will expand into about 80 liters. Now, these bottles have a volume of 0.5 of a liter, and therefore when that liquid nitrogen evaporates, it will occupy about 80 liters. It will generate a pressure of about 160 atmospheres. Now, these bottles, very clever though they are, made of brilliant polymers, they will just simply not withstand that pressure, and therefore they may explode. They don't always explode, but when they do explode, the noise is really quite substantial, and that's why, for safety reasons, I have put them into the bins. Now, that will continue to boil away. You may hear very loud bangs, so please be warned. But in the meantime, I'd like to show a couple of fairly obvious experiments with liquid nitrogen. The most obvious one being, of course, is to freeze some water. Water freezes at 0 degrees centigrade, and I will pour a small quantity of water into here and cover it with liquid nitrogen. So there goes our water there, and I shall now pour liquid nitrogen on it, and that will obviously turn the water into ice. Now, unlike the experiments which I did with my chemical waters, when I mixed chemical waters which were colorless together, and you saw a color change because a new substance
Or
was
can you hear
made.
me?
Here we have a totally different type of effect. You see, there is no color change at all. And that is because here we have a physical effect. The two colorless liquids, which I have mixed together, are now changing their state. They're changing, one of them is changing from the liquid state to the solid state, that is the water, and the other one, the nitrogen, liquid nitrogen, is turning from the liquid state to the gaseous state. So here we have the three states of matter in one very straightforward experiment. Now, as the liquid nitrogen continues to boil away, you may hear a slight crackling sound. Now, this is because when water freezes,
Test
it
1
expands
2
slightly,
test.
and as it expands, the crystals take up a greater area, and they push, a volume should I say, and they push against one another, and sometimes this may lead, it sets up enormous mechanical forces, which is what the crackling is about, and sometimes the beaker may actually crack. So we shall keep our eyes on this, allow the process to continue, and I can just hear the beginnings of a crackling sound. Now just top it up, make sure.
Okay, very good then. You're probably getting feedback through the loop. So, what can I help you with today? Our lag time is about 30 seconds, but I'm not sure how that applies to what's keyed in. Okay, well, when you key something in, I'll be happy and ready to answer questions at need. While I'm waiting, I'm looking over your answers to the two College Board questions. Question posed, are the AP practice problems that I put up today, are those from the videos? Yes, they are. Here, let me show you from where that came. Doesn't want to get large. There we are. So, let me change the layout. Okay, if you come in here on our page, I gave you some exam review type stuff. And if you look at the channel, if you go to the bottom of the channel, they're the practice problems. Now, the video was ridiculously useless.
This is time for you to work.
Hush.
This is...
The video itself was ridiculously useless. I mean, other than if you needed to stop a timer. But there was the nice stretch where they discussed submissions, and I think that was useful. It's worth folks looking through. But if you look down at the bottom, it tells you where to get access to the questions and the exam documents. So the questions I posted up came from Monday Sample FRQ 1 and 2. If you watch now, if you go in and are curious, you can go in, and I haven't posted this up yet, but they also put up the answers. I was obviously going to hold back the answers until folks that had an opportunity to do it. Obviously, if they've looked over this page, they know that they have access to that. So the gentleman goes through and explicates. What I like about it is he goes through and talks about the mistakes various folks made at different points in their work, whether this was each answer was a legitimate answer, or whether it was something that was not as useful or not correct. So hope that answers that question. I like this part though. He goes through and actually says, okay, here are 3 different answers. here are 3 different ways of approaching it. Are they good? Are they bad? And he goes through the entirety. This is something we would be doing in class if we were actually meeting, is grading each other's and grading samples based on the rubrics that they're presenting. Now, did you find you were able to get through the entire question in the 25 minutes available? Yeah, that question 2 was incredibly long, I thought, for what they expected you to get done in 15 minutes. Let me take a look at yours, I'm curious. Somebody else is on, so I'll just keep your personal answers private. Welcome. So whoever just joined us, you're welcome to chime in. No, it looks like I've lost all of you. I'm all alone. Yeah, it would appear. Okay, review letter F about dichromate. Okay. Colin, is that from the first problem or the second problem? Hold on, I'll pull it up now. Okay, it must be from the first one, since the second one... Wait, no. Yeah, it must be from the first one, because the second one doesn't make reference to that. Okay, give me a second, I'll pull that up. Yeah, I'm working on pulling it up. Just give me a moment. There we are. Okay, so the question at hand is going over letter F with the dichromate. So, student claims that experimental data indicates the reaction is first order with respect to dichromate. Do you agree or disagree? Justify your answer. Alright, so if we look at the absorbance changes, let me make this a little larger so you can see it more clearly. Alright, so it indicates the initial concentration is 1 times 10 to the negative third, and then it says calculate the concentration at the new time. So you'd be using the absorbance data. Okay. Interesting. Let me look at the rest of the problem. I'll read this over. Hooey. Okay. So I guess what we could do is we could look at the rate of change is about 2.3, 2.2, 1.4. The rate of change is not consistent, so it's not linear. If I would think, I mean, they've indicated that the test itself, you should be able to do this using only a 4-function calculator, but I would think you'd have to take natural log data. Now actually, no. Okay, for as far as F goes, it's not as all complicated as all that, because this is 78, After 3 minutes, it's 39. After 6 minutes, it's 19.5. So all you're seeing is you're seeing a decrease of 1/2 each time every 3 minutes. So you could say it's first order with respect to chromate or dichromate because the absorbance level is directly dependent upon the dichromate. Dichromate being an orange solution, which I think they mentioned, and then it changes over to a blue-green. So let's see something. Give me a moment. So my opinion is that the way in which to do that would be something along these lines. Let me show you this. Experiencing technical difficulties. Okay, desk and screen. Alright, so what I would probably do, I think this would satisfy them. If you go time 0.78 and then you indicate that at time 3 it's 0.39, you indicate that that is decreased by 1/2 the quantity or 1/2 the absorbance. Therefore, it should be 1/2 the concentration of dichromate. And then you say, okay, again at 6 minutes we're at 0.195. Again, we're at 1/2 the absorbance. Therefore, we're at, again, 1/2 the concentration. So I would say that would be sufficient explanation. Does that make sense? Okay, so the question posed on the stream is, I'm confused about the order of the reaction. So when something is first ordered, does it have its plot as natural log of concentration versus time as linear? Absolutely. But again, what I was saying was, in this particular case, we don't have to necessarily take the natural log because we're seeing a very specific half-life every 3 minutes. Which gives me a first order reaction, because I'm trying to think where it was we looked at those different half-life equations. I don't think they're on your reference sheet. Hold on. Give me a moment. I don't think your reference sheet gives the half-life equations, but I'm not certain, so I'm going to check. Okay. Okay, see, they only give the half-life equation for a first order reaction. In some of the tables that we've given out, they basically gave half-lives for the other two. But if it's a 0th order reaction, if it's 0th order, and we go concentration versus time, it'll go linear. So what that says is that it doesn't matter what that concentration is over the entire spectrum, it's going to have no effect on the rate at which the material decreases. Now in this case, that's clearly not the case because let me show you something here. Okay, because from here to here, a time of 3 minutes, we get a change of 0.39. From here to here, we get another 3 minutes, and we get a change of 0.195. And so clearly this is not 0th order because it's not acting in that way. It's not decreasing linearly. So what we're seeing is some sort of curvature. Now, first order versus second order, if we look at 1 over each of those, even though I know that these aren't concentration data, I recognize that these are absorbances, we can treat them like concentration data. In fact, when you did part E, you noticed that the absorbance versus the concentration were proportional, and I think that's legitimate. But if we do 1 over each of these, and even just stay with the 3 that we're working with, which we can do on a 4-function calculator, we get 1.28, we get 2.56, and we get 5.12. Okay, so just a quick check. If this is 1 over, these are the 1 over the absorbances, we notice real quickly that this change is 1.28, this change is twice that. So again, it's not second order because it's not linear when we do the 1 over data. So we're looking at this change. So the things that clue this in as being a first order reaction, the fact that each change is half as much, the fact that it's clearly not linear, because if that were the case, these data would be 0.78, you know, 655, 0.59, 0.39, and they would decrease, you know, like that all the way down. 0.19 would be the next piece of data. So this is clearly not linear 0th order. Sorry, I'm off screen. All right. So we've got a curved decrease. So I just real quickly, to check to make sure it wasn't second order, I just real quickly did the 1 over data, and I see again that this is not linear. This would be curved up significantly, almost exponential. All right. So to answer to kind of come full circle, if we look at the question basically says, student claims that this is first order. Then we just have to look at these data and see how they behave. Okay, so hopefully that helps. So another 30-second review. Since I'm doing this, and I'm going to put this up in case people can use it, I'll continue along. Basically, if it's 0th order, if we do simply concentration versus time, linear. If it's first order, concentration versus time will not be linear, but natural log of concentration versus time will be. If it's second order, again, that's not linear. Second order, this will not be linear, this will not be linear, but it'll be linear in this fashion. And then just by way of a reminder, if you look at the equations, this is just a y equals mx plus b equation just swapped around a bit. And you'll notice that the k value is the rate constant that we would bring in if we were writing the rate law thus. Hold on a second, let me just bring this up a bit. So all they're saying with those equations is that if we're plotting a 2 points on the natural log graph, natural log at some point equals negative kt plus the natural log at the 0th or at a different point. All they've done is rearrange that equation. This is simply y equals mx plus b. Therefore the slope is the inverse of the negative of the inverse of the rate constant. And so the rate for this particular one would be written rate equals K concentration of whatever that substance is to the first power, because it's a first order reaction. If you look at a second order reaction, again the equation that you see, it's nothing more than a y equals mx plus b equation, because it's basically 1 over the concentration at some point equals kt, notice that it's positive in this case because the slope is positive, plus 1 over the concentration at some other point. Okay, so I hope that's helpful. It's a good review of the basics of the different rate laws. And I will post this up. I'll segment this out, and you guys can look at this particular part independent of the others. If there's something in particular anybody would like me to review, I'd be more than happy to do so. But I don't have a specific agenda for these things. I would strongly suggest that you guys look at the updates that I've sent out over the last couple of days, because there's a lot of information there. Okay, unrelated to the practice, do we need to know the special electron configurations? Here's what I would throw at you. Let me pull up a periodic table. Ugh. Let me try a better periodic table. Let me get this out. Oh, sorry. Alright, so here's what I would suggest. Copper, the big... Where are we? The big thing with copper is that, again, and any of these fellows over here along this edge, is they're going to lose the 4s before they lose the 3d. Alright, that's important to know, because if they ask for the electron configuration of, say, copper 2+, it's going to be 1s, you know, all the way up to argon, and then it's going to be, if it's copper 2+, it's going to be 3d9. Alright, no 4s. So what that would look like for copper is, if it's copper 2+, it's going to be all of argon, and then it's going to be simply 3d9. Alright. And chromium, again, same kind of deal. If you're looking at chromium, it's kind of odd, because it is possible that they will... And the other thing you were pointing out with copper's oddity is that copper neutral, in point of fact, tends to be 3d10 4s1. Just weird. I can't see them testing that. I think they're going to have to be staying within the really broad spectrum material in order to get done. I mean, they didn't get terribly specific with the two things that I've sent you. They've argued that they're going to have, they haven't fully vetted the questions, but I think, again, I really can't see them getting into the nitty-gritty in 40 minutes, 45 minutes, 50 minutes. So, to answer your question, the special electron configurations, I strongly doubt it, but it is possible. I mean, again, with chromium, same deal, where it would be some sort of weird 3D model instead. So I wouldn't sweat that. Might be, you know, available to you, but I wouldn't worry much over it. Okay. Planning to take a picture, then use the CAM scanner to convert the image to a PDF. I would strongly suggest that. Okay, let me show you. If you haven't had a chance to look at Schoology today. Alright, I will probably also, if I get an opportunity, I might send out a video regards this. Let me get this changed over. If you look in the updates, they've been vacillating a great deal as to exactly how to submit things. So if you look in the updates today, what you're going to see is a series of discussions, not really discussions, but what was sent out by the guru or the head honcho of College Board testing. And there are a bunch of points that he brings up here. One of the first ones is how you can go about submitting your work. So let's talk briefly about that. Can a student submit a PDF of handwritten work? And the answer is now officially come out that you can upload a PDF of written work, but it has to be as one PDF. All right. So a great deal of the apps, I think, CAM Scanner should do that just fine. All right. Once the photos, now here's the thing, once the photos are saved, they're no longer considered photos, now they're documents. So if you haven't practiced submitting a document, you want to make sure that you're going into the correct space. If you haven't tried that submit thing, let me show you where to find that. I believe I placed it in updates, and I think I will also make that an assignment in the near future. Okay, so please, whatever method you're going to try, please go in, enter practice, or ask it nicely and enter practice. And then what you're going to do is you're going to be given the opportunity to, so just put in any garbage here. They really aren't looking for it. Just have to make it actually an email address, and then practice submitting. So that's right there in the updates. So that was the first thing. Hopefully that answers the question that was posed on the stream. But I would practice it and try it and make sure it accepts it, because that practice machine should behave in the way that the actual will work. Now, a bunch of other stuff. There was a lot of discussion on my listserv about using two devices at the same time. Now, the e-ticket thing. You're going to get an e-ticket, you're going to open it. They are saying to use that on one device. They had initially said that you possibly might be able to use it on two devices, but they've since changed their mind and said that you can only use the e-ticket on one device. Okay, so going back to the question in the previous, for those of you not familiar with CAM Scanner, you may want to look at that as a tool that you could use when you take a picture, and you should be able to, as Colin says in the reply stream here, you should be able to put all the PDFs together as one PDF and submit it. Practice the timing that takes. How long does it take? Because you're going to have literally 5 minutes if you start as soon as your timer turns red. If you decide to run into your submit time to work on your problem, you've got to be aware of how much time you have left, because if you don't turn it in and they don't see a reason that you didn't turn it in other than you ran out of time, you won't get credit. So, a couple other things. You can have two devices open. You can have two devices both logged in. You can, so some people are planning to just submit a JPEG. You can have the phone already logged in as well as have your computer logged in if you want to look at a larger version on the screen. If you're going to handwrite, now they're saying that handwriting can be submitted as a PDF. This is huge. Some of your phones are going to create what's called an HEIC file. Make absolutely sure your phone is not creating an HEIC file, because that won't be accepted. So make absolutely sure that you've gone through whatever steps are necessary to make your phone save it as a JPEG in order to submit it, or as he says before, you can convert that to a PDF if you know what you're doing. Bunch of people were talking about Apple Pencils, digital ink, equation editors. There's some specific information here as to each of those and how you would go about submitting those. The biggest thing is that there are two types of files. This last part's the important bit. Alright? There are two types of files that they can process. Text files. Alright? So you could save a text file as a PDF or a docx or a TXT file, or a photo file, JPEG or PNG. Make sure of how you're going to submit it and where you're going to submit it so that it goes through effectively. Alright? There's been a lot of discussion on the listserv about running over your time. That whole time is your time and how you choose to use it. I would just beg of you that you absolutely make sure that you leave yourself enough time, if there's a glitch or an issue, that whatever you do get done gets submitted. The one I gave out, excuse me, the one I gave out yesterday, that would be Tuesday the 5th, that one is representative of what you can expect on the exam. You can expect both parts to have up to letter J, as much as letter J for the 25-minute one, up to letter G or H for the shorter one. You're not going to get it all done, possibly. Get as much done as you can, pick and choose what you think you can get done, and make sure that much gets submitted, because you do not have to get it all done to get a 5. Alright, so I hope that answers that question effectively. But please, please, please read over the entirety of this. I know it's windy, but the simple fact is this all came out yesterday, and this fellow that wrote all this is like the head honcho, and he's made it clear of what is and what is not acceptable finally. We've been waiting for this for quite some time. That's why you're getting it now. Alright? And the other thing is, please commit the practice problems that I've expected. Alright, hope that helps. Other questions? Whoever else has come in, you're more than welcome to ask questions.
we continue to freeze our water. And I wanted to tell you that when liquid nitrogen was first made, at the end of the 19th century, it did set off an entirely new era in the history of technology, and that's liquid gas technology. And thanks to that, today we have frozen food, we have a huge number of all sorts of effects that we benefit from. Among them, of course, are refrigerators. Now, to continue then on our experiment, and also the science of cryogenics, to continue with our experiments with low temperatures, these, by the way, approximately 5 to 6 minutes, you'll hear the bangs, so please be warned. I'm now going to show you an experiment with a solid. Here we have a piece of rubber tubing, and it's elastic. The reason why it's elastic is because when you stretch it, it returns back to its original shape. Now, the reason why it's elastic is because I can hear the pressure being taken up, so you may hear a bang shortly. Now, the reason why it's elastic from a thermodynamic point of view is because it's very warm in here. And because it's very warm in here, these molecules in here have lots of energy. However, I will now place the rubber tubing into liquid nitrogen, and please observe carefully what happens. As we lower the temperature, and you'll notice this most interesting effect, you see, of a shower which is issuing from the end of the rubber tube. Now, why does this happen? Well, it's for the same reason that the bottles are exploding in there. And that is because as the liquid nitrogen boils fiercely when it comes into contact with the very hot rubber tubing, so it expands enormously, as I said, by a factor of about 800. That boiling, therefore, pushes the liquid nitrogen out, setting up a pressure forcing it out there. As you saw there, we didn't have anywhere to escape, and that's why the bottle finally gave way. Now let us inspect our rubber tubing which we have here, and let us see what has happened to the elastic property. It went in as an elastic solid, but now you see it's no longer elastic, and if I whack it one on this table, please watch carefully, then it will shatter into 1,000 fragments. Now, the reason why it shatters into 1,000 fragments is because at high temperatures, the molecules are all vibrating. We have lots of energy. The molecules of the rubber tubing have lots of energy, so they're all going around like that. But when you drop them into liquid nitrogen, there is very little energy, and so the molecules suddenly freeze. They go like this. They freeze solid. I'm, of course, being silly, but I'm illustrating an important scientific principle. Now, I wanted just to show you here, we're just going to see, in the meantime, I just wanted to show you our beaker has indeed cracked. There it is, there's a piece of glass has fallen away from it. And what that shows you is, it just shows you the huge forces, intermolecular forces, which are set up when water freezes. It freezes, the molecules rearrange themselves to form an open lattice. Now here I have a beautiful balloon, and why does it have the pressure? It has pressure inside it because the molecules of nitrogen and oxygen in here are moving around because they have lots of energy, because it's very warm. But if we reduce the energy by pouring liquid nitrogen over the balloon, then you'll notice a very, very interesting effect. So please watch carefully. I'm going to pour liquid nitrogen over the balloon, and as you notice, the balloon starts to contract. And as the balloon starts to contract, so you'll notice getting smaller and smaller, and it takes a very, very a shape which has there's no elasticity. It has completely collapsed. Now, why is this? Well, once again, it's the same reason. At the low temperatures, sorry, I think the floor's cracking underneath me. So everything's freezing all around, but we're still all right. Please look carefully. The balloon has now collapsed. It looks very sorry for itself. But if we allow it to warm up a little bit by shaking it up, throwing it up in the air in a very short space of time. Let's see if I can catch it. I'm sorry, it's escaping from me. It's escaping. As you see, it has been restored to its full shape. Now, why is that? Because at warmer temperatures, the molecules have more energy, and therefore they move faster and move more rapidly. Now, let's just carry on to my favorite topic, which is fire. This flame here represents one of the greatest traditions of the human race, and that is, of course, our ability to make fire. We know that in East Africa, where the first ancient civilizations were 100,000 years ago, people were able to make a fire and sustain a flame. I'm now going to just show you how 10,000 years ago, for thousands of years, flames burnt like this. This is a piece of cotton wool, and you'll notice it's a dreadfully boring flame. It just burns like this. Why is that? Well, because the cotton wool is surrounded by air. Air only contains 20% oxygen. It was only realized that air is a mixture of gases about 300 years ago, and we've been on this planet for 100,000. And once chemists have discovered the oxygen is the vital component of air that makes things burn better, they started either combining fuels with oxygen or mixing them with oxygen. And here I've got a piece of cotton which has been chemically combined with oxygen. Please watch how differently this burns. And we put it in here. And and it's blown the flame out. I knew it would blow the flame out, damn it. That's adding an extra 3 seconds onto my talk. Never mind, we shall quickly, I was ready, I had my matches. Now, what I wanted to show you, I've just shown you the world's first high explosive nitrocellulose or gun cotton. I would love to do an explosion with it, but I can't, we don't have the time, so I'm going to show you a propulsion. This here is a mortar. It's a type of device which is used for propelling fireworks high into the sky. I'm not going to prepare fireworks, I'm going to propel ping pong balls. So sorry, I've got 4 ping pong balls in my pocket here. I have a cage, gun cotton cage here, dropping it to the bottom, sorry. Has it gone to the bottom? I don't know, too bad. I'm going to force it to the bottom. I'm sorry, I'm struggling a bit against odds and against time. Let me just, there we are, I think it's gone to the bottom. If it hasn't, too bad. We're going to shove a fuse in there, and that will hopefully, when this goes off, we'll see it going up to we'll watch the ping pong balls fly out if they manage to reach the bottom. If they didn't, that's too bad. We won't see anything. But nevertheless, there goes our fuse. Hopefully, come on, catch fire. Time's running short. Dear me, this is a very bad piece of fuse. So I'm going to have to put my fingers on this, and there we go. Now, on to the final things here. Here we have, there we are. I don't know whether did anything happen? Yes, they walked. Now here we have, sorry, very quickly, we have here a balloon filled with hydrogen, caused a complete sensation among scientists. The lightest gas in the universe going on there. That's pure hydrogen. This is thunder air, aria tonante, a mixture of hydrogen and oxygen, and then it looks like that much louder. Now for my very fine work, I have here a mixture of hydrogen and oxygen. I have a fuse which I'm going to make here, and this will be my final experiment. We're going to have a thunder and lightning effect here. We're going to have a thunder lightning. Sorry, everything is going mad. Let's just get rid of this balloon. It's getting in my way. Now, here we are. I'm going to make up some flash powder, fuse powder. This is going to be, so to summarize, what have I been talking about? Chemistry. What have I been selling to you? Chemistry. In simple, direct language, chemistry for all. So here we go, fingers crossed, and there it is. So thank you very much indeed.